If you've ever just looked up at the night sky and wondered about the true limits of our universe, you are definitely in the right place today. Welcome to this explainer, where we are going hunting for a true cosmic monster. We are talking about Stephenson 218, the most massive star known to humanity. It is a star so incomprehensibly massive, it literally breaks our terrestrial understanding of size.
It's the ultimate question, isn't it? Just how big can a star actually get? Well, to wrap our heads around the mind-blowing scale of the universe's ultimate giants, we kind of need to calibrate our brains first. We have to start small. Well, small relative to the cosmos anyway.
Let's start right in our own backyard with our nearest neighbor. The moon is roughly 384,000 kilometers away. To put that into perspective, if you were to jump in your car right now and hit the highway at a constant speed of 100 kilometers per hour, it would take you over 160 days of non-stop driving just to reach it. And even from that distance, Earth already looks like this fragile little sphere cradled in the black void.
Now let's look at our sun. It is the undisputed heavyweight champion of our local neighborhood. If you were to hollow it out, you could comfortably cram 1 million Earths inside of it. That fiery behemoth provides absolutely all of our life-sustaining energy from an incredible 150 million kilometers away. But here's the crazy part. In the grand cosmic library, our sun is barely a footnote.
That brings us to Section 1, leaving the solar system.
Think about the Voyager 1 probe, launched way back in 1977. It represents humanity's insatiable curiosity. In 2012, it officially crossed the heliopause. That's the invisible boundary where our sun's solar wind finally gives way to the interstellar medium. Today, Voyager 1 is approximately 15.5 billion miles away from Earth. Yet, incredibly, its journey is just beginning.
Get this, even traveling at a staggering 17 kilometers per second, it would still take Voyager over 70,000 years just to reach our nearest neighboring star system, Alpha Centauri. It's a beautiful, yet kind of terrifying emptiness that separates the stars.
But actually, before we even truly enter that interstellar space, we have to pass the theoretical final frontier of our sun's gravity, the Oort cloud. This vast sphere of icy objects extends up to 100,000 astronomical units away. That is nearly 2 light-years thick. We are just a tiny, microscopic speck deep inside that bubble, which makes the gargantuan stars we are about to see even more special.
All right, moving on to Section 2, the giants we know.
So, if you look up at the constellation Orion, you can spot Betelgeuse. Located roughly 450 light-years away, this supergiant just completely shatters our sense of scale. It has a diameter over 750 times the width of our sun. It's this engorged, lumpy, boiling mass of plasma that's nearing the end of its life.
To truly grasp that size, imagine if we just magically swapped our sun for Betelgeuse. Its surface would stretch out so far that it would instantly swallow Mercury, Venus, Earth, Mars, and most of the asteroid belt. Our entire inner solar system would be completely engulfed inside this single star. It is a terrifyingly huge object. But guess what? It's not the biggest.
Which leads us to Section 3, introducing Stephenson 218.
Floating quietly in a star cluster, far, far from our little blue dot, this absolute titan sits in an incredible 20,000 light-years away. The sheer distance hides its staggering proportions from the naked eye, but our observatories have measured it, and the numbers will absolutely break your brain. Stephenson 218 has a radius over 2,000 times larger than our sun's. Remember how we said Betelgeuse would swallow the inner solar system? Well, Stephenson 218 extends far, far beyond that, completely eclipsing the orbits of the outer gas giants.
Let's talk volume for a second. You could fit 10 billion of our suns inside this single star. I mean, think about that. Not 10,000, not 10 million, 10 billion suns. It is an absolute monster of physical volume, dominating its region of space with a presence we can barely even fathom.
Now for Section 4, the cosmic monsters.
So what happens when massive stars finally run out of nuclear fuel? Gravity, which is arguably the most patient force in the universe, wins the battle. The core is squashed inward. If the star is massive enough, it becomes a neutron star, where the bizarre rules of quantum mechanics are literally the only thing preventing total collapse. It packs the mass of an entire star into a space the size of a city.
So we have two very different champions here. Stephenson 218 rules physical volume, but
If a dying star is too massive, even for a neutron star's quantum defenses, it collapses forever into a point of infinite density, a black hole. These dark remnants are the unbeatable champions of mass.
To understand this kind of gravitational dominance, let's use our Sun as one solar mass. Sagittarius A star, the supermassive black hole right at the center of our Milky Way, is about 6 million times that mass. But then, you have TON 618, weighing in at an unfathomable 66 billion solar masses. Its event horizon alone would completely dwarf our entire solar system. No contest.
How exactly does the universe create these dark monsters? It's the inevitable fate of the largest giants. First, the star exhausts its outward-pushing nuclear fuel. Then, gravity mercilessly squashes the core inward, and the mass collapses past a critical boundary called the Schwarzschild radius. The gravity becomes so insanely intense that not even light can escape. And just like that, a black hole is born.
And finally, Section 5. A tiny speck in the grand cosmic library.
There's a brilliant quote from our source material that says, "In this immense void, our galaxy home to our entire history is just a tiny speck among many, a single story in the grand cosmic library." When we look at objects like Stephenson 218, it is truly humbling. Everything we have ever known, every person who has ever lived resides on a microscopic fraction of a speck, floating in this endless ocean.
Which leaves us with one final thrilling question. What other impossible giants are hiding in the dark? Our telescopes are always peering deeper and deeper into the cosmic web. If a star that can hold 10 billion suns is just sitting out there, what else might we find tomorrow? Keep looking up, keep asking questions, and I'll see you in the next explainer.